Hello everyone. I hope you are all healthy and well. Welcome to the next talk in our Golden Webinars in Astrophysics series. Our speaker today is Meg Urry, who is Israel Manson Professor of Physics and Astronomy and Director of the Yale Center for Astronomy and Astrophysics. My name is Demetra De Cicco, and together with Thomas Puzia, we have organized today's webinars for you. As in our previous webinars, simultaneous language interpretation is provided by Patricia Gonzalez, who will be simultaneously translating for us in Spanish. En sus dispositivos pueden escuchar la interpretación al español de la conferencia al pinchar el botón de interpretación que se encuentra en la parte inferior derecha de la ventana de la aplicación Zoom y seleccionar español. We would like to acknowledge the generous support of the Center for Astrophysics and Related Technologies, also known as CATA for its Spanish acronym.
Thank you so much for all your feedback and comments. If you're watching a recording of this talk on YouTube, please leave your comments below. If you would like to support the Golden Webinar series, give us feedback or send us an email. If you have any questions during the talk, please type them in the Q&A window. You can also upvote questions and comment on them. We will select then the best questions for the discussion after the talk. The link of the live version of this video will be automatically taken down by YouTube shortly after the streaming is over. However, the final high-resolution version in both languages, English and Spanish, will be uploaded to our channel in the next few weeks. So before we begin, we of course will introduce our panel members that are with us today. Meg, of course, our speaker, Patricia, our interpreter, Demetra, and myself. From the Institute of Astrophysics, we have today my colleagues Ezekiel Treister and Franz Bauer with us today. Also from the Institute of Astrophysics, we have our postdocs, Paula Ronco, Elisabeth Artur de la Villamois, and Tim Hewlett with us.
We also have the great pleasure to welcome our guest panelists today. We have Paulina Lira, who is Professor of Astronomy at Universidad de Chile, Martin Elvis, Senior Astrophysicist at Smithsonian Astrophysical Observatory, Maurizio Paolillo, Professor of Physics and Astronomy at Università degli Studi di Napoli Federico II, Andy Lawrence, Regius Professor of Astronomy at the University of Edinburgh, Patricia Arevalo, Professor of Astrophysics at Universidad de Valparaíso, Thaisa Sorki-Bergman, who is supposed to join us soon, Head of Research at the Astronomy Department of Universidade Federal do Rio Grande do Sul, Gisela De Rosa, Roma Space Telescope Instruments Branch Manager at Space Telescope Science Institute, and Missy Bent, Professor of Physics and Astronomy at Georgia State University. And also, last but not least, we have our excellent Q&A managers, Ricardo Acevedo and Simon Angel. It is our great pleasure to introduce Meg Urry as our Golden Webinar speaker today. Meg received her bachelor's degree from Tufts University in 1977. She then got her master's degree in 1979 and her PhD in 1984, both at Johns Hopkins University. For the following 3 years, she was a postdoctoral fellow at the Center for Space Research of Massachusetts Institute of Technology. She then moved to the Space Telescope Science Institute, where she started as a postdoc. Then, in 1990, she became assistant astronomer and chief of the research support branch, then associate astronomer with tenure from 1995 to 1999, and finally, astronomer and head of the Science Program Selection Office from 1996 to 2001. She then moved to Yale University, where she is currently Israel Manson Professor of Physics and Astronomy and Director of the Yale Center for Astronomy and Astrophysics. She was also chair of the Department of Physics there from 2007 to 2013.
Meg's scientific research focuses on active galactic nuclei, the evolution of black holes and galaxies, black hole accretion, blazar physics, and AGN properties in general. Throughout her career, she has published over 330 refereed research articles on supermassive black holes and galaxies. She is known worldwide for proposing in 1995, together with Paolo Padovani, a unified model for radio-loud AGNs. The corresponding paper is one of the most highly cited review papers in astronomy, with currently clocking in over 3,400 citations. Meg is a fellow of the American Academy of Arts and Sciences, the National Academy of Sciences, the American Association for the Advancement of Science, the American Astronomical Society, the American Physical Society, and American Women in Science. She received an honorary doctorate from Tufts University, was awarded the Annie Jump Cannon and George von Biesbroeck Prize from the American Astronomical Society, and the Howard R. Lamar Award from Yale University. She's also known for her commitment to the cause of women and minorities in science, for which she received the Women in Space Science Award from the Adler Planetarium in 2010 and the Edward Boucher Leadership Award in 2015 from Yale University. So now we would like to hand over to Meg, who will tell us all about black holes, galaxies, and the evolution of the universe. Meg, the audience is yours.
Thank you very much, Thomas, Demetra, and everyone for the very nice introduction and the honor of giving today's golden webinar. I'm delighted to be with you. I'm going to start with a little bit of I guess, a quiz for the audience. This is my title slide written in the Galaxy font. If you aren't familiar with it, basically there are so many diverse galaxies in our universe that we can literally make a font out of them. And if you have trouble reading this, I do have a translation for you. This is what it says. But it's a lot of fun to write in galaxies. So if you get nothing else out of the talk, you should visit this website, writing.galaxyzoo.org, where the Galaxy Zoo crowd has created the font, and you can type in your name or a curse word or whatever you like and turn it into, you can Galaxify it. So I start with that because, in fact, the variety of galaxies is quite striking. Here you see a montage of very different looking galaxies. Some of them are disk-like, the one in the lower left, the one above it, this galaxy that is a bit dustier, the one in the upper right. These are disk galaxies, much like our Milky Way. Others are quite a bit rounder. Here's an elliptical galaxy. Here's one that has an enormous bulge with a little bit of a disk. As I'll discuss in the talk, all of these are telling us something about the history of the galaxy evolution, and something about when they last merged. And you see here in the upper left and middle right, you see some examples of pairs of galaxies that are interacting gravitationally and likely to merge in the near future. Regardless of their shape and color, which, as I say, tell us a lot about the galaxies themselves, we have discovered in the last 20 years that pretty much every galaxy above a certain mass hosts a very massive black hole at its center. By supermassive black hole, I mean a black hole that has a mass of 1 million to 1 billion times the mass of our sun. And the talk today will be about how we think these black holes grew over time and what impact they may or may not have had on their host galaxies. So let me start by talking about black holes. And to do that, we have to talk about gravity. The first theory of gravity was formulated by Isaac Newton more than 400 years ago. And interestingly, his very simple theory does an adequate job describing black holes if you're not too close to them. So I'll start with Newton. In his formulation, we can say that a black hole is an object for which its escape velocity is greater than the speed of light. Now, let me explain that escape velocity means the speed with which you must launch an object in order for it to escape a body's gravity. For example, if you went outside and threw a ball up in the air, it would rise up and then it would fall back down because you can't throw it that hard. But if you threw it a little bit harder, it would rise higher, and so on. Throw it harder still, it will rise higher. If you had, a rocket-powered arm, you could perhaps launch it hard enough, fast enough, for it to reach a distance infinitely far away, come to rest at a distance infinitely far away. And that speed with which the speed needed to reach infinity is what's known as the escape velocity. So a black hole is an object for which the escape velocity, the speed you would need if you were on the surface of the black hole, the speed you would need to escape it, that velocity is greater than the speed of light. And as Einstein told us many years later, as far as we know, no particle, not a matter particle or a photon of light, can travel faster than the speed of light. That means black holes, nothing escapes a black hole, not matter, not light, hence the name black hole. These objects were actually thought of quite a long time ago by Pierre Laplace and also John Mitchell, a British astronomer, who in 1783 wrote about the idea of a dark star, an object whose escape velocity was greater than the speed of light. Basically, we wouldn't see the dark star. He had another insight, which was very interesting, and it's in this text that you can't read, but anyway, he said, if there exist in nature any of these dark stars, bodies whose light could not arrive at us, we could have no information from light, yet if any other luminous bodies should happen to revolve around them, we might infer the influence of the central one. And in fact, this is the technique that's been used to demonstrate really the best case of a black hole anywhere in the universe, and that's the black hole at the center of our galaxy. My friend Andrea Ghez, who recently got the Nobel Prize for this work, along with Reinhard Genzel, has been mapping the orbits of stars around the center of our galaxy for the last 20-some years. What you're watching here is a video of those orbits. The very center of this image is where the center of the galaxy is and where the black hole in the center of our galaxy is. And you can see that some 24 stars have been very carefully mapped over this time period. The physics students will notice that the inner stars move faster than the outer stars. That again is easily explained by Newton's gravity. But the key thing is that each single orbit constrains the mass and the location of the black hole. And with several dozen stars, it's now well established that there is a black hole at the center of our galaxy that weighs about 3 to 4 million times the mass of our sun. So that brings us to Albert Einstein. He had a very different concept of gravity than Newton. Newton's idea was that there were two masses and a force between them. So any two masses feel a force between them. Einstein instead thought about gravity as a deformation of space-time, that mass deforms space and mass moves in response to those deformations of space-time. We won't go into the theory today. It's probably too complicated for 1 hour, but I will give you the highlights. His theory actually predicted the existence of black holes. And moreover, in fact, the first solution to his equations of general relativity was the case of a single mass alone in the universe. And that was solved by Schwarzschild. So Schwarzschild found that this would be a singularity in space-time, and that the black hole would have a radius that is 2 times the g is the gravitational constant from Newton's gravitational laws, times the mass of the black hole divided by the speed of light squared. So this is called the Schwarzschild radius. It's appropriate for a non-spinning black hole, but it's basically the size within which the escape velocity is greater than the speed of light. It's also interesting to note that the radius is proportional to the mass. So you often hear that black holes are very dense, that, you know, a teaspoon of a black hole would weigh many hundreds of thousands of tons. But this is really true only for small black holes. As the black hole grows in mass, its radius grows proportionately. So its density, its mean density, declines as the square of the radius. And in fact, the mean density of a black hole that is 100 million times the mass of the sun is about the density of water, 1 gram per centimeter cubed. I always think that's interesting to tell people. If you fell into a supermassive black hole, you wouldn't even notice it. You wouldn't notice any difference from being outside the black hole to being inside, because the gradient of the gravitational field is quite small. Okay, those are just fun facts. So let me give you some examples of what black holes might be like. Again, all of these are allowed by Einstein's theory, although not all of them are observed in nature. If you took the entire Earth and squished it down into an object the size of a sugar cube, that would be a black hole. If you took a very heavy star, maybe 10 times the mass of our sun, and squished it down into a black hole, its radius would be 3 kilometers, about the size of the town I live in, much smaller than Santiago though. Our Milky Way, as I told you earlier, has a black hole that is about 3 million solar masses, and that its radius is a few percent of the size of the solar system. The most massive supermassive black holes have radii that are a few light hours. That is, light takes a few hours to travel, would take a few hours to travel from one side to the other. I calculated, just for fun, what would happen if you took a 100-kilogram person and made them a black hole. They would be smaller by many orders of magnitude than the smallest particle we know. But only the stellar and the supermassive black holes have so far been observed in nature. Now, no matter can escape the black hole, and no light can escape the black hole, but there turns out there's plenty of light from the region around the black hole. That's because, that's because matter is trying to fall into the black hole, and before it falls in, it heats up and radiates a lot of light that we can observe. So there are 3 principal ways we can detect the presence of a black hole. One is to effectively weigh it by looking at the orbit of bodies around it. So this is the experiment that Andrea Ghez and Reinhard Genzel have spent their careers doing. And I showed you that a moment ago. A new way that's really quite new is we can image it, at least the 2 nearest black holes, or sorry, not the nearest ones, but there are 2 black holes we can currently image with the Event Horizon Telescope. You may remember 2 years ago, the big announcement of the image of the radio galaxy, the black hole at the center of the radio galaxy M87. This is the image. This image was on the front page of the New York Times, and 100% of the readers who took the weekly New York Times quiz knew that was a black hole. I was so impressed by that. You know, I do the quiz every week, and usually 90% or so of the people will know what some celebrity was doing last week, and maybe 50% will know some international news that happened. But I have never seen 100% on anything except the black hole at the center of M87. So it's impressive that that a scientific result made such a deep impact. In any case, I'm going to show you a video from the National Science Foundation that illustrates what we're looking at here. This image was taken, as I say, with the Event Horizon Telescope, which is a synthetic telescope made up of radio telescopes around the world, such that the effective aperture is the size of the Earth. And here is the video. M87 is a radio galaxy with jets coming out of it. Its black hole is 1 billion solar masses, several billion solar masses. And so it's quite large. And this radio telescope was able to image the light around it. Photons flying in the vicinity of the black hole are bent by its gravity and focused so that we see a ring of light. So the ring that you see in the image is caused basically by gravitational focusing of the black hole. And the shadow in the middle is where the black hole is, although the shadow is bigger by a factor of a few than the black hole itself. And thank you, NSF, for your money. Okay, so that's a really exciting new way to look at black holes. But as I say, at present, only 2 black holes are accessible with that telescope. The third way, oh, and I've skipped LIGO completely, which excuse me. But anyway, the third way is to observe the light that comes from accretion onto the black hole before particles fall into the black hole. And that is the work that my research group and many on the panel actually have been doing for some time. So the idea is that matter is trying to fall into the black hole, but because the matter has angular momentum, it has to settle into a disk, and there is friction in the disk that allows the matter to collide and some of the matter to gently move toward the black hole. And as it collides, it heats up, basically, and glows. So back to our picture of the different galaxies in the world, in the universe. I want to bring in the second point about what is the effect on galaxies. As these black holes are growing, they aren't born at millions of solar masses. They start much smaller, and over their lifetimes, they accrete matter and generate a lot of energy that goes out into the galaxy. And so there are reasons to believe that deposition of energy has a profound effect on galaxy evolution. To put this in context, I'm going to show you the history of the universe in one slide. So this is a cartoon adapted from the WMAP group. Here we are looking at time moving from left to right, from the Big Bang, 13.7 billion years ago, to the present day. The size of this shaped thing has taken out the overall expansion of the universe, the linear expansion of the universe, and just shows you what is above or below that. And the idea is that maybe a few 100 million years after the Big Bang, the very first stars form. They were unusually massive because there was only hydrogen and helium at the time. And so they left behind remnant black holes that were also unusually large, perhaps 100 solar masses or so. Those occurred at the densest points in the universe, and so they are naturally at the center of where galaxies were going to grow. So it's natural to think of these black holes as being the central supermassive black holes of the future, with the galaxies slowly forming stars around them. And that's the story I'll tell you a little bit about. Now, why do we think the growth of black holes has an effect on the evolution of galaxies? First of all, I've already told you every galaxy seems to have one in its center. So this is a global phenomenon. Second, we know that black hole growth and star formation track each other in time. So they're at least happening at the same time, and probably in the same galaxies. The third reason is an interesting correlation observed about 20 years ago between the mass of the black hole at the center of the galaxy and the velocities of the stars around in the galaxy. This might seem expected, except that the black hole is very massive, but much, much less massive than the galaxy. Maybe 1/1000th of the mass of the galaxy. So most of the stars in the galaxy don't feel the gravity of the black hole at all. Their motions respond to the mass of the galaxy itself. So it's strange that the stellar motions should, in a sense, know about the black hole mass. So this relation was interpreted as a sign that the growth of the black hole is mediated somehow by the mass of the galaxy. And the last reason is really that theorists really need the energy injection from black hole growth in order to prevent the formation of too many stars. It's very easy to create a simulation of the growth of structure in the universe over billions of years, and things look pretty good, but if you just let the computer run with only gravity and adding some dark matter, you get too many stars in the present day, and energy from black hole growth would disrupt those. One of the most attractive demonstrations of this is this computer simulation from the Illustris group. Here you are looking at the dark matter density as time goes on, and in the lower left of the movie, you should see the age since the Big Bang. So this is about 1 billion years after the Big Bang. The matter gets clumpier and clumpier under the influence of gravity, and stars and galaxies will begin to form at the densest parts, have begun to form at the densest parts. In just a moment, the color scheme will change. And then we'll be looking at the temperature of the gas in this simulation. The gas is about 10% of the total mass. The dark matter dominates. Here you see what look like bombs going off. Those are growth spurts of black holes in the centers of galaxies. And that energy is deposited into the galaxy and the intergalactic medium, ionizing it and changing the history going forward. If you look closely, you may also see some little flickering, much smaller flickering. Those are supernovae, explosions of individual massive stars in the galaxy, which also delivers this kind of feedback. And just for completeness, I'll let this go because it's quite beautiful. The colors will change again to this purple scheme. And what you're looking at now is the chemical composition of gas in the universe, where white is highly enriched and dark is not very enriched, because the universe starts out as almost all hydrogen with some helium. And only after matter has been processed through the centers of stars do we get the other elements, carbon, nitrogen, oxygen, et cetera, that are very common in every other star and galaxy we see today. Okay, so this has taken us up to 11, 12 billion years, and I'm going to skip the last 1.5 billion years because you know how it turns out. Okay, so we were interested in the question of how much energy do black holes actually deliver to their host galaxies? In other words, how much mass do they accrete, and when does that happen? And in effect, how many black holes are doing this as well? So I'm going to tell you now about what my group has done. In particular, most recently, the Accretion History of AGN, or AHA project, in which we carried out a multi-wavelength census of black hole growth. And then at the end, I'll tell you a little bit about this idea of feedback, of the AGN feedback onto the host galaxy. We've looked for evidence of it and what we found. Okay. So the first thing is we decided we had to do a multi-wavelength census of black hole growth involving hard X-rays, because they very efficiently detect growing black holes. Oh, I've neglected a terminology point. So AGN is the acronym for active galactic nucleus, or nuclei, and it means a galaxy whose central black hole is growing rapidly, is accreting a lot of matter. So those are identified as AGN as opposed to normal sleeping galaxies. So hard X-rays find AGN efficiently. Infrared radiation is a calorimeter of all the absorbed UV, ultraviolet, and soft X-ray light, which is reprocessed. And the optical is very useful for observing the host galaxy and separating it from its nucleus. Now, in the early days of studying AGN, most surveys were optical surveys. And most recently, the Sloan Digital Sky Survey found more quasars than any previous or subsequent survey has done. But optical surveys miss obscured quasars. Unobscured quasars means there's nothing in the, not much dust or gas along the line of sight. If there is a lot of gas or dust, the light from the AGN or the quasar can be obscured and you just don't see it, or rather you identify it as a galaxy rather than an AGN. So adding the X-rays and the infrared changes this, helps us see obscured AGN. Now, why might we think there are obscured AGN? Here are 3 reasons. This is a cartoon of what we think the inner structure of AGN is, and a black hole with an accretion disk surrounded by various structures of gas and dust. The important point is that for looking at this object from some directions, for example, from the side, looking through this donut of thick gas and dust, one might not see the bright emission from the center. That's called unification. We also know that as you go to higher redshift, which is to say further away, therefore the younger universe, there is more dust and gas, molecular gas and stars forming. So you might expect even more obscuration toward higher redshift. And the third reason is really probably the most defendable one, which is that X-ray astronomers had observed something they call the hard X-ray background, which is actually the summed emission from all AGN. This is a plot of what that background spectrum looks like. If you just point your X-ray telescope at the sky and ask for what the diffuse emission is doing, this is intensity versus X-ray energy from 1 to 100 kilovolts. And you see that there's a very peaked spectrum, which we now know is this summed emission from all AGN. But for my present purpose, let me just say, if there were no obscured quasars, the summed emission from all AGN would have to be a horizontal line in this plot. The curvature is telling us that we have absorption at low energies. And that was really a very strong clue that there must be a lot of obscured AGN. Okay, so we go to do our survey using NASA's great observatories, the Chandra X-ray Observatory, the Hubble Space Telescope, the Spitzer Infrared Space Telescope, and the European XMM Newton X-ray Telescope. We also use ground-based telescopes such as Keck and in fact Subaru. So these are the 2 Keck domes, identical 10-meter telescopes, and the Subaru dome behind, which we also used. This is on the summit of Mauna Kea on the Big Island. And our goal was really to identify how much obscured black hole growth there is, because we suspected it was substantial. You know, in the US, we do a census every 10 years. We count all the people. Well, we try to count everybody in the country. And we too are doing a census. We're not trying to count every black hole, just a representative sample. So it's unlike the US Census in that regard. But imagine doing a census where you only counted people who lived on the even side of the street, say. So you missed half the people, or you only counted people who lived in cities instead of in the country. It's like that. Our census was designed to find black holes that were not found by previous census efforts. Okay, one more thing I want to explain is that we did a wedding cake survey. The idea is that you combine surveys with different depths and areas. So let me explain why you would want to do that. The idea is to have a sort of small survey that's very deep, bigger survey that's deeper, bigger, deeper still, and shallower. And the biggest survey is very shallow. And the reason is that I'll show you, never mind. I'll explain now. So this is a diagram of the luminosity of the objects detected in a survey versus their redshift in log-log space. And I'm showing here just one survey, the Swift-Bat All-Sky Survey of AGN. And you see that there's quite a good correlation here. This is observationally induced. On one side, on this lower side, we have a flux limit. That is, we cannot see objects fainter than this line. If they're fainter, they would be lower in luminosity at a given redshift, or higher in redshift at a given luminosity. So we cannot see, this is sort of outside our ability to see this corner. What people don't notice quite as often is there's also a limit on the upper side due to the luminosity function. In principle, you could see anything up here. It's bright enough to be seen, but bright luminous objects are very rare. And so as you, at a fixed redshift, as you go up in luminosity, you run out of objects in the volume of your survey. So any one survey just basically gets a band in this plot. When you combine different wedding cake layers, you'll see you can get more of the space. So here's one more way to explain this. This is what we call luminosity function, the number of objects as a function of their luminosity per unit volume. So the density of objects as a function of their luminosity, that's the way to say it. And typically in nature, luminosity functions are something like this. They don't have this, lots of things at low luminosity. There are lots of objects at low luminosity, few objects at high luminosity. You see this all the time. There are lots of low mass stars, few high mass stars. With AGN, it's the same thing. So imagine doing a survey which has a very small volume. Then you'll only see, because you have a small volume, you can only see the most common objects. So a small volume survey only sees where you have a lot of objects, okay, high density, and that will cut you off at a low luminosity. High luminosity objects will be too rare to be found in that volume. But if you do a large volume survey, then you can reach high luminosity. So that's the idea of the wedding cake. We combine surveys that are very deep, sort of pencil beam surveys like GOODS, larger, Cosmos, etc. I'll show you those now. And putting them together allows us to fill out the redshift luminosity plane. Now, GOODS actually preceded AHA by a fair amount. This is the Great Observatory's Origins Deep Survey, which I had a hand in designing. It combined the power of NASA's great observatories over a large, deep area for the time. And we were looking at the origins of galaxies, but also trying to add a letter so that we didn't look obnoxious. So the GOODS survey was actually what Ezekiel Treister did his PhD thesis on. So I'll forward all questions to him about that. GOODS was about 1/10 of a square degree, so very small compared to Sloan, which is 10,000 square degrees. Cosmos is about 15 times bigger. This is the X-ray image of the Cosmos field, and Martin Elvis had a great deal to do with this, this field. So again, he can answer all those Cosmos questions. And then we did the Stripe 82 survey, X-ray survey from Yale, and that's another factor of 20 or so larger at present. And finally, the Swift-Bat survey is all sky. So putting those together, we can fill out this luminosity redshift plane and separate evolutionary effects, i.e. things that depend on redshift, from luminosity effects. Okay, so the tool we use to analyze our multi-wavelength surveys is called a population synthesis model. These were first developed 30 or more years ago by looking at the X-rays. Basically, you take the distribution of objects as a function of their luminosity and their redshift and their absorption, and you connect them to X-ray spectra, and you try to fit the X-ray background. We also tried to fit everything else. The number of X-ray sources you see is a function of their flux. We then incorporated multi-wavelength. In fact, Ezekiel's thesis was to incorporate the multi-wavelength optical and infrared data and satisfy all of those constraints, how many objects you see as a function of their brightness, et cetera, et cetera. I'll give you the bottom line of that work. It was quite controversial at the time, but we claimed that 3/4 of all black hole accretion is obscured and had not previously been seen. That compared to the Sloan Digital Sky Survey sample, there are 4 times as many, at least 4 times as many black holes as we thought before. In the last 5 years, much more X-ray data have become available. I don't expect you to read this table, but the point is to say, instead of one little good survey, there's a tremendous amount of new data. And so my graduate student, Tonima Anana, undertook to redo population synthesis model, and I'll show you a few of her results quickly. Again, reminding you, the ingredients are the luminosity function, the X-ray spectra, and the amount of obscuration that we assume. And the reason she did this model is the existing population synthesis models could not fit the data, could not fit all these data. One of the things we tried to fit was the X-ray background, the spectrum, which I showed you before. Here are a few examples of the other best known population synthesis models. WADA's model here, which you see misses badly at the low energy end and also not so sure at the high energy end. This is the Aird et al. Model, which again, if you hit it at one end, you miss at the other end. And then here's Tonima's model, which fits everything. I should be fair to the previous works. We were trying to fit data that they had not yet seen, right? That was obtained after their work was done. So it's not surprising their models didn't fit those data, but Tonima's model is the only current model that fits all of the existing data. And in addition to the total intensity, which is shown by this solid line, you can see broken down into 3 bins of absorption where the components are. This very peaked component is the Compton thick objects, the objects with column densities above 10 to the 24 atoms per square centimeter. Okay, just to show a few more of these kinds of things quickly, this is the number count, so number of objects as a function of their X-ray flux in log. And this is a compilation of all the available data. Up here is the deepest X-ray field, the Chandra Deep Field South 7 megasecond field. This is new compared to when Aird and WADA did their work. And also our Stripe 82 data, which fills in at high fluxes. And if you look at, this is the WADA fit, misses at the low end. The Aird one does as well. Tonima, sorry, this is the Buchner. This is the Buchner luminosity function, which also fails. And here is Tonima's, which goes through all the data. So it isn't so much the fit to any one of these curves, but the fact that you can fit all of them simultaneously, which is the hard thing. Here's another example of the density of Compton thick objects as a function of their flux. You see that the Aird and WADA models are several factors of several too low. And here is the Anana model fits well, the recent NuSTAR data, Cosmos Chandra data. This is the Swift BAT data, same idea. Let me speed this up. This is my favorite. Okay, this is my favorite. This is a plot from Ryan Hickox of the resolved, that means the detected objects in hard X-ray new star band compared to the total X-ray background. So he's resolving about 40% of the background. And he went to the existing population synthesis models and tried to explain what he was getting and couldn't get it to fit at all. And then he heard that Tonima had done this model because she'd already actually submitted the paper. So he asked her to calculate what she would predict he would see with NuSTAR from her model, using the area observed and the flux limit and so on and so forth. And this is what her curve was, not adjusted in any way to fit his data, done completely independently. And here is where Weta was in a slightly different band. Let me be fair, this is for the Chandra data. Here's where those Chandra points are, also from Ryan's work. You see the Weta model doesn't fit the Chandra data either. And here is where Tonima's, not fit, but Tonima's prediction is for those data. So her model seems to do a very, very good job of describing all of the X-ray data on AGN that we seem to have at present. Okay, let me move along. I will skip this and do just the last bit. To summarize what I've told you about our survey, to give you the highlights, most black hole growth is obscured. And so in order to count it all, and in order to understand how much energy is being deposited in galaxies, you have to include these obscured AGN. They're the dominant source of light in the universe. Sorry, aside of accretion light, I should be careful. There's more light from star formation. With this AHA wedding cake survey, we sampled the full AGN population. We need to go to larger area. We need a bottom layer. We need a larger area and shallower survey to get the highest luminosities. We're working on that. And our population synthesis model not only explains all X-ray constraints, but we can compare the total light produced to the local mass in black holes and derive an efficiency for the accretion, which is quite high, nearly 40%, which implies that black holes are spinning rapidly. So the next step of this work will be to add the infrared and optical constraints, as Ezekiel did for his thesis, but with many, many more data sets than we did then. So it's complicated. Okay, so now I'm just going to do a short discourse on what we've been able to see about the effect of AGN on their host galaxies. And to sort of telegraph the answer, if you haven't the stamina to listen to the whole thing, we've had a surprisingly hard time finding evidence, direct evidence for feedback. It looks as if the majority of galaxies are not strongly affected by AGN at their centers. So why do I say that? Here is the explanation. And this is work that really Kevin Shawinski started and many others have worked on. So in order to tell this story, I'm going to show you a bunch of this kind of diagram. This is a color mass diagram for galaxies. The color on the y-axis, this is a U band minus R band, so ratio of ultraviolet to red flux, but basically red is at the top and blue is at the bottom. And along the x-axis is the stellar mass. The contours you're looking at are the million or so galaxies in the Sloan Digital Sky Survey. Now, this was observed almost 20 years ago, that galaxies seem to come in two colors. There's a red sequence and a blue cloud. And the thinking here is the blue cloud is where stars are forming. They form, with a range of masses, but the most massive stars are very, very blue and they live a short time. So when they burn out, you're left with the red stars. So basically, as stars age, they move up in this diagram. As a stellar population ages, that's the way to think of it. The blue stars burn out and you're left with the red stars, so you move up in this diagram. And of course, you could have galaxy mergers. And when that happens, you move to the right. But you notice there are very few objects in this middle ground in what's called the Green Valley. And so the idea for some time has been that you have some kind of mergers happening between these star-forming galaxies that triggers an AGN. The AGN quenches the star formation, that is to say, stops the star formation in its tracks, and then the galaxies rapidly age up to the red. So that's kind of like the standard picture of galaxy evolution. But so AGN feedback is supposedly critical in moving galaxies rapidly across the Green Valley. And what Kevin named the paper, Kevin said, this is a red herring. I realize that may not translate to Spanish. I don't know whether you have this saying, but in English, we have the saying, red herring means a distraction, a misdirection. And so Kevin called this paper, The Green Valley is a Red Herring, which was kind of cute, but I blame him. What was this about? Let me explain. So first of all, I will confess, as someone who was educated in physics, that I never cared at all about galaxy morphology. I thought the black hole is in the center of the galaxy. It doesn't care what the galaxy morphology is. I shouldn't pay any attention to it. But Kevin came to work at Yale, and he was an Einstein fellow there. And he had been involved with Galaxy Zoo, which is the citizen science project that put all the galaxies online for volunteer citizens to classify their morphologies. This was all conceived in a pub in Oxford some afternoon when they'd had a few too many beers. And it's a hugely successful project. And here I'm just showing you an example of a set of what they call early type galaxies. On the top row, I would call them spheroidal galaxies or elliptical galaxies. They're very round. And then on the bottom row, you see what they call late type galaxies, and I just call disk galaxies. So spirals and S0 type galaxies. And they're organized from blue on the left to red on the right. So their database includes 1 million galaxies, each of which has almost 100 classifications from independent people, which is way better than one astronomer poring over image after image and putting their bias in there. When you have 100 people classifying, you can get a very clear, well, let's say it this way. This sample, the top row and the bottom row, are the galaxies for which 80% of the classifiers or more agreed. So it's a very clean sample. Now, why am I showing you this? Because we went back to the color magnitude diagram. I say we, Kevin did this. We went back to the color magnitude diagram and decided to look at it separated by morphology. And that really made a huge difference. Here is the diagram for spheroids on top and disks on the bottom. And now this sort of bimodal picture is gone. You see a lot of red spheroids. Well, we knew this, but okay, a lot of red spheroids and some blue ones. And then in the disks, you just see a lot of blue disks, and maybe some of them get red at some point. So there's no obvious green valley here and no obvious place. Okay. I would say this, let me simplify things. This diagram with the spheroids at the top right, this actually does resemble the standard picture. If two blue disk galaxies merge and form a spheroid, that's how these blue galaxies come out of nowhere, okay? And then if they can evolve very rapidly, whoops, sorry, go back one. They can evolve very rapidly to the red, perhaps aided by AGN, then they end up in the red sequence. So this diagram supports the standard picture, but this is less than 20% of local galaxies. are in this diagram. Most of the galaxies are disks, and they sit down here, and they seem to have a very slow evolution, which is unaffected by AGN. In fact, anything that's green here is actually, if you look more closely, just a blue disk with a red bulge. So it's not actually a population of stars turning green, it's a mix of bulge and disk. And the time scale for this evolution, I'm not giving you every detail, but the time scale is many billions of years, whereas these time scales for the spheroids can be quite short, much less than 1 billion years. Interestingly, for the disks, we can do one more diagnostic diagram, and that is here where we separate, well, we did for all of them, we separate low mass on the left, low mass halos, and high mass halos. Okay, look at the left first. This looks a lot like what I just showed you. The spheroids are evolving from the blue, the disks are just sitting there not doing much. But when you look at the high mass halos, the disks, the spheroids look the same, the disks look very different. At high halo mass, suddenly we have a lot of red disks. And what this is implying is that the halo mass influences the evolution, not AGN feedback, but the halo mass. Once it gets high enough, gas stops accreting into the galaxy. So the gas supply is turned off, so the star formation turns off, and then the galaxy becomes redder. Okay, so one caveat about all this work that Kevin did is that it's all at redshift 0, which is not where most stars form or most black holes grow. So we also looked at redshift 1, and this is work done by my graduate student at the time, Mary Powell, now at Stanford. I'm not going to show you all her diagrams, but basically she sees the same kinds of diagrams. The spheroids look very different from the disks in exactly the same way. They seem to quench quickly, maybe helped by AGN that are triggered by mergers. I will say that a larger fraction are in this bin at redshift 1 compared to redshift 0, but it's still a minority. It's not the majority of galaxies. Meanwhile, the disks appear to evolve slowly and not to have been involved in mergers. So the bottom line from this work is that AGN feedback is not obvious in most galaxies. And yeah, and I'll also say that mergers don't seem to be a big factor in most galaxies. Even at redshift 1 and redshift 2, most AGN are hosted in disk galaxies, which means they have not undergone a recent major merger. And mergers, the black holes seem to grow sort of slowly, and the galaxies evolve slowly. Mergers are probably much more important for high luminosity AGN, i.e. quasars, and Ezekiel Trester has done some very nice work on this. They aren't numerous, these high luminosity objects, but they do account for a fair fraction of the black hole mass. So we still need to understand them in order to understand all of the black hole growth. So from all this work, I would say, yeah, many galaxies quench slowly. And so black holes may not be as important for galaxy evolution as we sometimes suggest. Okay, that is the whole story I was going to tell you guys. And so I hope that made some sense. And I would be delighted now to answer questions or to fop them off on the panel.
Fantastic. Thank you very much, Meg. We're gonna take a 2-minute break, and I encourage you all to have a look at the Q&A. There are some great questions there, and so we're gonna come back after the music is over. All right, so let's get back to the Q&A. So Meg, thank you very much again for a beautiful talk. That was a wonderful overview of the AGN field. And really exciting stuff, I think, lying ahead. So I want to start with the first question, motivated by one question that popped up at the very bottom here. Well, not anymore now, in the Q&A window by Santiago Arce. And he's asking, what will happen if two black holes crash in our own galaxy, maybe a white hole? But I want to take this a little bit further. So, of course, black holes grow in mass, right? And they grow by merging with other black holes. Do you think there is maybe like different modes of growth rate and activity, AGN activity, let's say mechanisms that you could disentangle by having this, last parsec problem or last parsec state, multiple black holes in the centers of galaxies that you could sort of tease out of the data that you already have?
Oh, that's a really good question. So first, let me say that I think the mergers of black holes in the centers of galaxies is a really important and not yet well enough understood issue. I should have said that the fourth way of detecting black holes, of course, is gravitational waves, which has been a tool now since the detection of two merging black holes by LIGO in 2015. For the kind of black holes we're talking about here, the very massive ones, we need a different interferometer. The European LISA is an example of one that could probe that space. And I think we don't know enough about whether, we know that galaxies merge and therefore their black holes must end up in the same galaxy. But what exactly happens to them there is unclear. We think they may sink to the center of the galaxy and then literally merge. People have been looking for dual nuclei in galaxies and finding some, but not super many. So does that mean they've already merged? And then there's some recent theoretical work that implies there might be wandering supermassive black holes out in the outskirts of galaxies, which are in low enough density regions, they wouldn't accrete brightly enough to be seen. So there, I think that's a hugely rich area. Now, the question was, can my survey address it? And the answer is probably not. We probably need the gravitational wave interferometer in space to do a bang up job on this.
Okay, so let's go to Demetra.
Yeah, so now we have Ezequiel who would like to ask a question from the Q&A.
Yes, it's actually not my question, but a question from Álvaro Valenzuela, who's a very talented PhD student at our program. And so he's wondering, or my interpretation of his question is mostly about the observed cosmic downsizing of black hole growth, right? We know that the most massive black holes form firms and earlier than the least massive black holes. So he was wondering, why is that? And I guess you mentioned a little bit towards the end of your talk, but it might be that there's more than one mechanism to trigger black hole growth and how they're related. And his final question is, and I know you will like this part of the question, is what do we need in order to unravel this? I know you have some very good ideas about it.
Okay, well, it's an excellent question. I completely neglected to mention that some initial black holes may form through a different channel than what I talked about. I talked about the most massive star, first generation of stars. There may be what are called direct collapse black holes, which happen rarely, but in special circumstances and can start out very massive. And those should occur again, at the densest parts of the universe. And therefore it's natural for them to be associated with the most massive galaxies and with the earliest formation. So that's one, people speculate about that. I think there are some data, but nothing that yet tells us how the bulk of black holes originated. I think we need much more data at high redshift, both X-ray data and other data, in order to do the census at high redshift. We have, so far, we've gone back 12 billion years from the present, but not that last billion where a lot of the action was happening. I don't know, Ezequiel, you may want to add something yourself to this answer.
Well, my guess is, so a lot of the growth happens through basically secular processes, right? So it's very steady, very slow, and that's mostly what your talk was about, right? That the very slow growth that probably is not causing much of the feedback. But there's also, or there should be some very rapid episodes where you form, where mostly high mass black holes grow, and that happens mostly at the high redshift 2 and above or so. So the evolutions are different for the low mass and the high mass black holes.
Yes, yes, yes. I'm sorry, I missed that was the point you were asking. Yes, and that explains maybe why the red and dead galaxies are all forming at high redshift.
Okay, now we have a question asked by Misty.
Hi, Meg. You talked about two very interesting studies towards the end of your talk today, and some of the takeaways were quite interesting. And I wonder if you can tell us a bit about whether they actually agree with each other. So one study seems to indicate that there's a tendency for very high spins in black holes, and the other seems to indicate that it's the halo of the galaxy that is quenching the gas flow to the galaxy, and therefore might be affecting what's happening with the black hole more so than mergers, for example. Do the numbers work out for those two things to agree? Is that indicating enough secular evolution in the galaxies to spin up the black holes to very high rates? Or is there maybe some tension between those two results?
Oh, that's a really good question. I actually haven't thought about it before, but I would say that there's plenty of matter in any of these galaxies to spin up any black hole to its maximum spin. I think the only thing you need in order to have high spin is not too many mergers. That is, to have the mergers not be too frequent, because mergers can mess up, right? If you add two angular momenta that are different, you can de-spin something. Otherwise, just wait long enough and every black hole will spin up. So I think there's no contradiction, but yeah.
Okay, Thaisa is next.
Thaisa, you are
You're muted.
Okay. Hi, Meg. How are you?
Hi.
Nice to see you. Great talk. And I just would like to check with you about the feedback, because as far as I understood, you were arguing that the feedback from AGN is not that important, or not as important as we thought about before, but only because of the diagram that you can explain with separate clouds of these galaxies and the red galaxies, only because of that. Do you think it's enough evidence to say that we don't need feedback from AGN for the galaxy evolution?
You know, that's a really good question. I mean, I think, and also something I didn't say, you know, the time scales over which galaxies evolve are quite long, because stars evolve over long time scales, and we're just seeing snapshots of the AGN. So there's an inherent difficulty in trying to correlate the two, which I acknowledge. I would say that, you know, AGN feedback is a very easy tool to put in your computer simulation, right? Yeah. It's a very easy knob to turn, and it works. But that is not sufficient to say that it happens. And there are other knobs you can turn, like halo mass, which do an important job. And of course, supernovae, which we all know are already important. So I think the jury is out. I would say for high mass black holes, luminous AGN, the ones that clearly are in mergers, I think there's good evidence that feedback is happening and is important. But your sort of garden variety galaxy, like the Milky Way galaxy, I don't think the evidence is very strong.
Yeah, I would concur with that, because we have made some studies of ionized gas, and the ionized gas, you know, velocities and feedback, at least kinetic feedback is always very low. But you know, we always say that there are other ways of feedback, but you know, evidence from observations are a bit sketchy also. Thank you.
Thank you.
Paulina, you're next.
Yep. So we have a question about the unified model, and brings in one of the most famous diagrams in in the history of astronomy, and is your diagram from your review paper, right? With the torus and the accretion disk and the narrow line region and the broad line region. And the question is, where is the broad line region? Because they say that in some of these sketches is within the ionization cone, and in some other ones it looks like they are to the side of the accretion disk. So this person, Heitor Robleto Ruz, is asking which of these representations you think is most appropriate.
I see. Well, first of all, should I show that diagram? I don't know if it's worth it.
Yes, you must.
Let me see if I can quickly move there. And there it is. Okay, so here's the cartoon. First of all, let me assure you, this is absolutely not to scale or even realistic in any way, as everybody knows. So what this is meant to be is that these gray things are gas clouds, which are photoionized. And the ones that are down here inside the torus are the broadline clouds. And the ones that are much farther away, and therefore moving much more slowly, are the narrow line clouds. So I guess they aren't terribly differentiated. The colors are different, but you can't really tell. They aren't terribly differentiated, but these are the broad line clouds, which you only see face on, and these are the narrow line clouds, which you can see from any direction. That's the plan. And I should also say, so in gross character, I think this picture is correct in that there are a lot of objects that very much how they appear very much depends on the orientation with respect to us. But there are also huge intrinsic differences between one AGN and the next. And there are surely, differences that have nothing to do with orientation. So this is an oversimplification. Some people want to shoot down this idea, assuming it says that the only difference between any AGN and any other AGN is orientation, which clearly is not correct. So.
But do you think the clouds are above, as in your cartoon, or they are like contained in the same plane as in the same plane of the disk and the torus?
Yeah. I think the broadline clouds are quite close to the black hole, and either they could be in the accretion disk or they could be above it. I don't think that's a settled deal, although some of you are far more expert on that than I. And the narrow line clouds are just very distant, so they're just. That's the two populations. I'm worried I haven't answered you properly.
No, that was fun. Thank you.
Okay.
Next question is from Andy.
Hi, Meg. I was fascinated to see that you don't see much evidence for feedback. I quite like that because it's always kind of worried me. I just don't understand it. But earlier on, during your talk, you talked about the evidence that people have quoted for years about the so-called M-sigma relationship, that big black holes go with big galaxies. There's a tight relationship. So if that's not caused by feedback of the black hole on the galaxy, what, in your opinion, is the cause of that relationship?
Oh, good question. Good question. I don't know that I have a great answer, but I will say that some years ago, I'm forgetting who did this. Maybe you can help me. But somebody showed that if you did only mergers, that is, black holes only grew by merging, galaxy merge and the black holes merge, no accretion, zero accretion, you would get the M-sigma relation, right? Makes sense. So it certainly need have nothing to do with M-sigma does not tell you have some kind of accretion and feedback.
Yeah, I must look that up. That sounds good.
It could be just like the central limit theorem, essentially.
Yeah, I believe that was Knut Jahnke. Was
it Knut?
I think so. Yeah.
Okay.
Just to comment on Andy's question, though, is that you explained that most of the galaxies are secularly growing, right? They're not merging, and so in that case, we still need something to lock in that for most galaxies.
Yeah, fair enough. Yeah.
Okay, Patricia is next.
Yes, thank you. So I wanted to ask a question actually by Paula Sanchez, a colleague in Chile. So she's very impressed by how well ANAMA's models fit the X-ray observations. And wanted to know a bit more. What's the main difference between, for example, her models and previous models?
Yeah, I think they're just a little more complicated. They most resemble Buchner's models in that he did, rather than an analytic form of the various functions involved, he used a probabilistic approach. And then on top of that, Tonima put a framework. Okay, how to say this? In the end, you're trying to fit many different pieces of data to well, a much smaller number of parameters, but it's complicated. And for a few weeks, maybe months, she would come and show me plots and they weren't good enough. You know, the fits weren't good enough. And she was doing all the adjusting by hand. So she got annoyed with me telling her to go do a better job. And she went away and wrote a sort of a machine learning wrapper around everything to adjust the parameters automatically and get the best fit without her messing with it. And I think that's in addition that she was fitting new data that the others didn't have, she managed to get everything to fit, which was definitely not something you could do just by tweaking parameters. So it's complicated. And now the important thing is that we need to add the optical and infrared constraints, because that could change the picture. We have those data, we know what they are, and they have to simultaneously fit there. So that's another huge effort coming.
Isabella, will you ask next question?
Sure. I'm going to ask a question by Clara Hoffman. She's interested about black hole growth, and in particular, she's asking if there is a limit in its growth, like what's going to happen at the end if the matter in the universe is finite. So in the end, is it going to end up all in one black hole?
Oh, that's a good question. So first, there's no limit in the sense of, you know, there's not like an upper limit to the mass. You know, there's not like a black hole gets so heavy and then the chair breaks. You know, it's in principle, they could get much bigger. In fact, we found some years ago with Benny Trachtenbot at Keck, we found a black hole that was 10 to the 10th solar masses at a redshift of about 3 inside a galaxy that was only about 100 times more massive than that. So weird things happen. But what happens in the long run? Black holes are hungry. They have a lot of, you know, they exert a lot of gravitational pull, but it's really hard to make matter fall into a small object because it has to lose so much angular momentum. And so really the trick is, how can it lose the angular momentum? And for that, you need other matter around to collide with. So if you wait long enough, probably the whole universe will end up in black holes, but you'd have to wait a really, really, really long time. And dark matter doesn't help us here, at least as far as we understand it. Like most of the matter in the universe is dark matter, but it is not collisional. It's not colliding with itself or with other matter. And so it doesn't help any matter lose angular momentum and fall into the black holes. So yeah, so if you waited long enough, like an infinite amount of time, everything would be in a black hole. But for a long, long time, the dark matter is just going to be trucking around, not falling into anything. I think that's the answer. I don't know. You guys should correct me if you have a better answer.
Well, now Ezequiel wanted to add something related to the previous question.
Yeah, it was actually more about the previous, about Patricia's comment. And mainly something to remember, the key difference in Tonima's work actually came also from the NuSTAR data. Back when we did the X-ray background modeling, only 1 to 2% of the background at very high energy was resolved. And now, as you show in your plot, and mostly thanks to NuSTAR, is 40%. And that makes a huge difference in constraining the number of quantum fixed sources. So NuSTAR, I think, was interpreting the NuSTAR results, which Tonima did, I think is key in her model.
That is a really important thing to say. Thank you for bringing that up, because before, people were just using the integrated X-ray background to constrain the amount of Compton thick objects, and you could trade off the number versus the amount of light coming from each, if you like. And whereas NuSTAR is actually literally detecting these objects individually, and that makes a huge difference. I totally agree. Thank you.
Maurizio, next.
So Meg, I had a question about connecting the stellar mass black hole and supermassive black hole, because the stellar mass evolved much more rapidly than the supermassive black hole, and there have been many suggestions trying to identify, to unify the behavior of this source. So do you believe that the AGN evolve on a slower scale, but in the same way of stellar black hole, they go through the same phases, and that basically everything is driven by the same physics, or there are some fundamental differences?
Oh, that's a very interesting question too. Well, I mean, I guess black holes are very, very simple objects, and so the size and their properties. Well, and we can say that stellar mass black holes and AGN share a number of pretty obvious similarities: the accretion disk, the temperature scaled by the mass, etc. One big difference is the stellar mass ones are fed by the companion star, so that's quite a different geometry and changes things. I don't really know. I mean, as far as I can see, we see a lot of commonality. I guess an unspoken question is, why don't we see intermediate mass black holes, which I think is an open question, but seeming increasingly unlikely. Again, I think here the gravitational wave information is going to be extremely important. I found it really fascinating that the first LIGO event was a collision of two black holes of about 30 solar masses. To me, that seems so unlikely. 30 solar masses is a little too big. If it's normal stellar evolution, they should be sort of 10 solar masses or less, okay? But then, okay, they could have grown from their 10 solar masses by accretion, but then why would you have two that had grown exactly the same amount? That seems really weird. And then it's implying that this 30 solar mass kind of thing is very common. I don't know, I just thought that was a key. That was a key result that I have not fully digested and have not heard a good explanation for yet. If they had seen 200 solar mass things colliding, you could say, okay, those were primordial black holes, and they were in an undense region or whatever. But so I think that might be where we unlock the understanding of how the full spectrum of masses is connected or not.
Misty would like to ask another question. Go ahead, please.
Hi, Meg. So this question actually is from our audience, from Alvaro Valenzuela. And Alvaro would like to know, harking back to your fun facts at the beginning about densities of black holes, what are some consequences for having a small mean density for really supermassive black holes, and compared to a low mass, high density black holes? And in particular, what came to mind for me was tidal disruption events and maybe some observational consequences there.
Yeah, absolutely. I mean, the only effect really is the gradient of gravity at the horizon. So it's a little misleading to say big black holes have the density of water, because of course they're not uniform. They don't have uniform density. As soon as a particle falls into the black hole, it heads for the center, and the center is very dense and the rest is not so dense. Nonetheless, I think a tidal disruption event that Misty just mentioned is when a star passes by a black hole, say, and is tidally disrupted. That means when an object, when the object is of a size, I'm not saying this well at all. I think I've been talking for too long, but I'll try. Tidal disruption means the near side and the far side are pulled on differently by the black hole. So it stretches the object and basically disrupts it. Some of the older members of the audience may remember the comet that fell into Jupiter about 30 years ago. That was tidally disrupted essentially by Jupiter. So and stretched apart into bits, and then it fell in. The same thing can happen when a star passes a supermassive black hole. There, I think the star is big enough that the gradient of gravity across it is substantial. What I was thinking about when I talked about not feeling it as a person is when I was a graduate student at the Goddard Space Flight Center, somebody brought in the National Enquirer. Okay, the Americans would know what this is. This is a trashy newspaper with crazy made up stories that they sell in the supermarket. And this one had a story about X-ray astronomy, believe it or not. It said that because the HEO-1 satellite had supposedly found a great mass of gas and black holes and other things. And so it was a story about the agony your family would feel if you were pulled into a black hole and ripped apart like, you know, by the tidal forces, which we thought was hysterical. Unfortunately, I've lost the article. But anyway, it wasn't true, because if you fell into a big black hole, your body is small compared to the black hole size. And so, you know, if you fell into the black hole, one side of you would not feel a different gravity than the other side of you. So you wouldn't be ripped apart. But if you fell into a smaller black hole, if it were small enough so that the size of your body was closer to the size of the black hole, then one side of your body would feel a very different force than the other side of your body. That's the tidal disruption. That's being ripped apart by a tidal force, a force that's different on either side. So that's what I always think of when I think about the mean density of black holes and what their effect would be on your body. It's what the National Enquirer was predicting in the 1970s or whenever that was, and that will not happen near a big black hole. A person will not be tidally disrupted. A star can be tidally disrupted, but a person, no.
Andy wanted to add something. Yes, please go ahead.
Yeah, I was just going to add something about tidal disruption events, because I love them, because they're my fave thing at the moment. But I think it relates to your answer just now, Meg, about whether black holes get bigger and bigger and bigger. And the answer you gave was that it's really hard to get matter down the plug hole, as it were. So eventually the gas immediately around in the disk just empties out. And then there are these sort of dead, quiet black holes just sitting there, and they're not growing, and because it's really hard to get the gas down. Meanwhile, there are stars, that are just zipping to and fro, and for 10,000 years, so what? They just zip past, nobody ever notices, and then one day, one poor little star just goes close enough that it goes, and then it leaps back into life, the black hole temporarily, and you didn't know it was there. So yeah, so it's just really fun, I think, but it does fit nicely with the answer you gave earlier.
I'm glad you brought that up, because it's a perfect probe of dead black holes, right? If you want statistics on how many of those are there and what are their properties, it's almost the only way to survey that, to do the statistics of tidal disruption events. So yeah, very interesting. But you have to be very patient, Andy. I'm not sure I'm patient enough to wait for those things to happen.
Well, you know the answer to that, Meg. You have to watch 10,000 at once.
Yeah, I have another question from the audience. So it's by Chentao Yang, and he's asking, this kind of harkens back to something you commented on during your talk. I think Kevin Schwinsky came to Yale and got you interested in morphology. And so he's actually asking about, are there any insights that you could have between, that relate the properties of an AGN and the properties of a black hole, supermassive black hole, and the dynamics of the galaxy, how the gas is made up, what it's actually doing at a given time?
Yeah, so well, I would say the first thing that morphology is telling us is the recent merger history. So big honking disks did not have recent major mergers. And so what their gas is at the center is the function of lots of local physics at the center of the object. Whereas I think when you go to an elliptical galaxy, then you're looking at something where there's been a lot of disruption and potentially a lot of that can stimulate accretion onto the black hole. So I think that is telling us something, but not in detail. I think some of you, Thaisa, and other people, have done detailed studies of centers of near enough AGN where you can actually do spatially resolved things, and maybe we learn more from that than from the large scale morphology. But I think the morphology is good for statistical analysis of big samples, and sorting big samples into how they might have evolved.
Thomas, you wanted to ask a question too, right?
Yes, so I found this one really interesting here from the University of Groningen is apparently listening in, and they're asking, AGN feedback can be positive and negative in theory, they say. Are there any contradictions that they can coexist together?
No, it's a very good point. Yeah, and I am not an expert on this. I've read the papers, and there are papers that have found both. So if you have a very active AGN, maybe it's stopping stars from doing things, but maybe also it's causing stars to do things, like pressure waves can cause compression of gas to create to stimulate star formation. And I have seen work that describes both of these things happening. So in principle, I think they can both be happening, particularly because we know AGN are not spherically symmetric, right? If they were, then maybe it would be harder to gin up both processes at once. But given that radiation can go out in some directions, gas flow can go out in others, accretion can happen in others, I see no reason why you couldn't have both. And maybe that's drowning out the signal. I don't know if that was the intention of the question, but maybe that's preventing us from seeing what's happening.
Okay, so last question from the Q&A by Terry Bollinger, who is asking, do you have any observations regarding the Mond background fitting into your conceptual world?
I have not worked on MOND, the modified Newtonian dynamics, which is a theory that essentially fits the diminished, it's about rotation curves in massive objects and showing that gravity may weaken as you go to weak gravity, weaken more than the Newtonian amount as you go to weak gravity. I did have a postdoc who worked on this for a while in globular clusters. And what would I say? I would say, one thing in science is that we should really be open to new ideas, regardless of what the fashion is. So we should be open to ideas that do not fit the current paradigm, because in fact, all great leaps of knowledge are essentially turning one's back on the current paradigm. I just reread this book about Galileo's Daughter by Dava Sobel. If you haven't read it, it's a great book. Galileo got in a lot of trouble because his observations supported the Copernican idea that the sun was at the center of the universe, not the Earth. And people really, really clung to the idea that the Earth was stationary and everything, all the stars revolved around it. So we didn't, if you like, we didn't make scientific progress until people were willing to give up that wrong idea and accept the fact that, in fact, planets orbit the sun. So we have to be open to these ideas. On the other hand, if you're going to write papers about MOND, I think you have to recognize that there's a lot of skepticism about it, particularly because it's a semi-empirical model. It's not really motivated by fundamental physics. So I think you have to invoke it when it's pointing out something that can't be explained in other simpler ways, kind of an Occam's razor kind of thing. So that's a wishy-washy answer, but it's because I think we should be open-minded, but I haven't been convinced it's important. idea yet.
All right. Yeah, I like the Occam's razor approach. It's a good one, but definitely a future field to explore. Okay, so let's wrap this up here. Thank you very much, Megan. This was a wonderful talk. Thank you, panelists, for joining us.
Thank you. Thank you, Meg. Thank you.
Thanks to the audience as well for tuning in. It was, I think, a great success today. Please be so kind, fill out again the survey after the webinar is over. And we announced the next talk in the Golden Webinar series, which will be on April 9th and will be given by Pavel Krupa. And his talk will be about From Belief to Realism and Beauty. Given the non-existence of dark matter, how do I navigate amongst the stars in between the galaxies? So very fitting. And okay, everyone, thank you so much again. Please stay safe, stay healthy, and until the next Golden Webinar in Astrophysics. Bye, everyone.
Bye.
Bye.